And before we start our presentation, I would like to take a moment to thank our client Fluence and especially Taylor for guiding us and for choosing this research. You have truly been a mentor for us through this process. And of course, we would like to thank Professor Tafus for always being there for us when we had any questions. And we are honored to also have here Mr. Addison Stark, former RPE Fellow and Associate Director of Energy Innovation at BPC, as our guest speaker. So before we delve, sorry, I don't know where my clicker is. Sorry. Before we delve into the topic, I will want to take a moment to introduce myself and the team. I am, oh, okay, what happened? Sorry. I am Irina.
I'm Catherine.
I'm Po-Kuan.
Tristan.
So today we will present to you an introduction into Water-Energy Nexus and go over our methodology and regional analysis finding, and we will conclude with our recommendation. We will welcome your questions right after our speakers' remarks. So what we tried to do in our research was to raise awareness on the vulnerability of the energy system to the availability of water, and to examine the issues and propose potential steps to be taken in the next decade. As you can see in this infograph, water is absolutely necessary, is absolutely essential to produce, use, distribute energy, especially in electricity generation. So our research approach was to identify the thermal and hydro capacity that is under water stress, and to see how different climate shocks can lead to curtailment of that capacity. And we did that under different curtailment scenarios. So just to give you a quick overview of our research, what we concluded is that 25% curtailment of the capacity under water stress would be a worst case scenario for all of the regions that we focused. So we focused on 4 countries: US, Australia, France, and Spain. So what we came up with was a timeline that highlights the order in which this country would have problems in meeting their peak demand with their dispatchable capacity in a 25% curtailment scenario. So as you can see, right now, Australia and Texas might have problems in meeting their peak demand with their dispatchable capacity, followed by Arizona in 2020, California 2023, Spain in 2025, and France and Pennsylvania sometime after 2030. And this problem of water stress and curtailments has already happened multiple times in the regions that we have studied. I'm not gonna go too much in that. I just want to highlight France's case that in multiple years has had curtailments of their nuclear generation due to water stress, and the most recent one was actually last year in 2018. However, I do want to emphasize that this is a prevalent issue. This is not something that is just in the region that we have focused. So I could add to these cases Brazil, Colombia, or Kenya that have had power shortages due to water stress. So as you can see, this is an urgent matter that needs to be addressed. So as you can imagine, this type of curtailments do result in, they do have an impact on the overall energy system, as well as on the well-being of the people impacted by it. So the consequences that we concluded on was that you would have a less resilient grid, less reliable grid, and there's also going to be financial cost incurred both on the utility side and also on the customer side. And I know some of you might be thinking, oh, well, you know the drought is coming, you can just import more electricity. Well, that is true, but that could be just a short-term answer, because once your neighboring countries that are exporting to you or your neighboring regions have the same problem due to climate change as you, and at the same time, that puts the entire system at risk. So right now, I will let my colleague Po to kind of emphasize the urgency on addressing the water stress, water-energy nexus.
Okay, thank you, Irina. So, as what Irina said, water plays a role in energy sector and the electricity sector. But why we care about water? It's like something, an issue, and it's something urgent that we need to pay attention. Actually, yes. This is the water stress problems all over the world. We got a world map from World Resource Institute showing a water stress area in 2020. The orange and red dots are those regions affected by water stress, and the darker the color is, the more severe the problem is. And as what Irina says, with the climate shock and climate change, things could become even more severe. The World Resource Institute gave this result after assessing the water consumption, water demand, water supply, and withdrawal, taking into consideration of climate and social economy scenario. And with their projections, in 2030, you will see the water stress problem will expand. More regions will fall under the water stress areas, and you can see the more dark red points appear all over the world, especially in Southwest United States, Chile, MENA area, Northern China, Southeast Asia, and Australia are among those regions will be suffering the most. So what does this mean for the energy sector or the electricity generation? This comes to our major topic here, the Water-Energy Nexus. When it comes to this term, you might find many definitions, but at this research, we are looking at the water intensity of the energy. That is, the amount of water needed to generate a unit of energy. And in this research project, we are trying to answer this question, how water scarcity or water temperature can affect electricity generation. So with this definition in mind, I will let Tristan to talk more detail about the concept behind it.
Thank you, Po. So now we're going to focus on how do we use water in electricity generation. So first of all, we use for thermal power specifically and hydro. We use a ton of water, obviously, to create steam to turn turbines, but then we need a lot of water to cool the systems because producing electricity generates a tremendous amount of heat. And you also obviously need water for hydro, and the water is in the reservoirs. I think that one's pretty straightforward. So what type of technologies are there to cool the systems? There's several, but some are more deployed than others. In the US, in the last decade, the most deployed one was recirculating systems. Then there was the once-through, cooling pond, and then you can barely see it, the dry-cooled systems, even though that's the most efficient way to cool systems because it uses the least amount of water. On the other hand, it's the least deployed. So this is maybe where we can move forward with. Different technologies uses water at different rates. So nuclear and coal power use a lot more water than, for instance, gas turbines. This is on average. Power plants are very thirsty. They use a ton of water. So quick facts, it uses between 125 to 190 billion gallons of water daily in the US. And that's a weird number to put in perspective. That's around 190,000 to 290,000 Olympic swimming pools used daily for cooling systems. So it's a ton of water. And this is important because climate change is happening. And so because of that, it impacts the electric grid. So first of all, there's an increase in heat waves. Increase in heat waves means there's going to be an increase in peak demand, electricity demand in the summer, namely due to increase in use of AC. And because of that, you need even more water to cool the plants. On the other hand, if you have climate change, there's been a lot of cases of drought. So you have a drop in water availability, and due to that, you also have an increase in water temperature. And for electricity, what that means is because it basically means there's not going to be enough water for cooling systems. The water is going to be too warm to cool the systems themselves, which means they need even more water to cool their thermal plants. And the water to discharge back into the rivers is going to be too warm. And that can impact biodiversity and ecosystems. I just want to put the idea of climate change here. It's really important because there's been a lot of cases. Texas had the 2011 drought, which was a huge deal. Eastern Australia, it's been the driest starting since 2013 that it's ever been, so now I guess it's the new norm. And we know in Europe, Southern Europe, there's been also a lot of cases of drought. So this is an idea that's very important for us to deal with. And now I'm going to let Catherine explain our methodology for our work.
Thank you, Tristan. So in the following, I'm going to talk about the methodology of this research, and I will explain how we drive the conclusion of the central question of our focus mentioned by Paul earlier, that is how water scarcity and water temperature increase can affect electricity generation. So in the first step of our research, we utilize Resource Watch. It's an open source data visualization platform provided by the World Resource Institute. We combine two maps together. The first one is the global power plant database with the projected water stress areas in 2030. Specifically, the scenario for the projected water stress area is for the RCP 8.5, business as usual scenarios. And having the idea of what are the power plants that might located in water stress area in 2030 and 2020 and 30. We utilize ArcGIS to extract relevant data of these power plants. For instance, their name, their generating capacity, and then what's their sources used. Having all this data in mind, we move on to do our own calculation. Before we start our calculation, we made a few assumptions to our research. The first assumption we made in our research is we only calculate the power plants that its generating capacity that is larger than 100 megawatts, and we only consider power plants that utilize fresh water. Regarding the newly added capacity, we utilize the same level of stress as baseline in our calculation. There are indeed a few limitations in our research. The first one is regarding the retirement schedule, as this might be affected with policy reasons, and also with the peak demand forecast, as this will be changes with economic growth or with more climate change effect. Having all this data and all this idea in mind, we move on to our calculation, and the two main calculations we have here. The first is the megawatts in water stress area, and the second one is the reserve ratio. So what is reserve ratio? The reserve ratio we are referring to here is that we put the denominator, peak demand in the denominator, and then in the numerator, we put total dispatchable minus curtailment rate times total stress. We set the baseline as 1, so if the calculated reserve ratio value is lower than 1, then this implies that the region might not be able to meet its electricity demand with its dispatchable capacity. Moving forward, let's dive down into regional analysis. I think this is the part that you guys feel excited about. So we will go over with US first, and then followed by Australia, Spain, and France. So I will start with Texas. So in 1990, Texas legislature restructured the power market in Texas. And since then, ERCOT managed the power system in Texas. Currently, they manage 90% of the electricity market there and serving around 23 million of consumer in their region. So in one of the report they released in 2018, ERCOT provide a forecast for Texas electricity mix and peak demand for the next 10 years. And we can see in the 2020 scenario, natural gas accounts for the largest share, still accounts for the largest share in Texas, followed by coal and nuclear. And among which 89% of the total dispatchable capacity will locate in water stress area. Moving on to 2030, Texas follows the trend of increasing deployment of gas, solar, and wind, and phasing out coal utilization. So you can see there's a slight change with the coal percentage in the electricity mix. And in 2030, 88% of the total dispatchable capacity, 88% of them will locate in water stress area. Here is the reserve ratio in Texas. So you can see as the peak demand is 1, you can see clearly even without any curtailment happen, it might be very unlikely for Texas to meet its peak demand with its dispatchable capacity. You may wonder why this is an issue, why the reserve ratio for Texas looks so terrible. And the reason is that currently Texas already need to rely on its non-dispatchable capacity to meet its peak demand. So if we only take dispatchable capacity into consideration with water stress curtailment happen, the situation worse. There are indeed a few federal and state level action in place to address this issue. So in the federal, there is a national pollutant discharge elimination system, which provide permits to pollutant to release in the water. And regarding the state action, Texas has regional water planning process starting in 1997. And specifically in its 2017 report, it's the first time that they mention drought and drought response. And this is because of the 2011 severe drought event happened. Texas also has a water code, and this is provide with drought annex that lists down the responsibility of different entities while drought event occur. Texas also on the way to scaling up renewable sources. According to its report, it plans to have 5 gigawatt of wind in operation by 2020. It's also worth mentioning that there's a newly introduced bill named Energy and Water Research Integration Act, and this was introduced in January this year. And this bill is calling for integrating energy and water research. And this bill was introduced by a representative from Texas. So you can see Texas is aware of this issue. Moving on to Pennsylvania. So Pennsylvania is under PJM's jurisdiction. And according to the report released by them, natural gas, nuclear, and coal are the three main sources Pennsylvania is using for its generating capacity. And among which 51% of the total dispatchable were located in water stress area in 2020. Moving forward, Pennsylvania also follows the trend of increasing use of natural gas, and it also has a RPS standard in 2021. So if we take into account that all these things happen on time, we can see in 2030, it's natural gas, nuclear, and coal will also account for the largest share. And 44% of the total dispatchable will locate in water stress area. So this is the reserve ratio in Pennsylvania. And the only drop point, and you can notice here in 2021, that it's likely that they might have issue with their to meet their peak demand. And then the reason is that in 2021, Pennsylvania plans to retire one of its very big nuclear plant. And that plant accounts for, the generating capacity of that power plant is approximately 1 gigawatt. But overall, you can see Pennsylvania has a pretty high reserve ratio, and that's also the reason that it's under PJM's jurisdiction. And PJM has a history of having pretty abundant reserve margins. And Pennsylvania also have a few policy action in place. So the first is the Great Lake Compact, which lists down the responsibility of 8 states using the Great Lakes water. And in this compact, they mention energy impact should also be addressed. And there's also a RPS standard I mentioned earlier. So this is about the analysis and our methodology. I will let Irina to talk about our analysis for California and Arizona. Thank you.
Sorry, short people problems. Thank you, Catherine. So Arizona, looking at the electricity mix, you can easily understand how water stress can affect electricity generation in Arizona. And that is because they are highly reliant on natural gas and coal and nuclear. And if you look on the right, you're going to see 87% of their total dispatchable capacity is situated in a stress area. So that creates an urgent problem to address for Arizona. By 2030, they will retire about 2.3 gigawatt of coal and 1.3 gigawatt of gas, but that still leaves Arizona highly reliant on dispatchable generation. So also in this case, I would want to mention that while we were researching on Arizona, what I realized is that most of the power plants that are under stress use the water from the lower Colorado River, which has decreasing levels, has recorded decreasing levels for the past years. So this is definitely a problem that Arizona has to address in their resource planning. Looking at the reserve ratio, like I mentioned at the beginning, a worst case scenario would leave of 25% curtailment of the dispatchable capacity would leave Arizona in vulnerable to meeting their peak demand with dispatchable capacity by the end of the year. However, the most likely scenario for Arizona from our calculation would be a 15% curtailment, and that is mostly driven by hydro and nuclear or coal curtailment. As I mentioned, one of the reasons are the decreasing levels of the Colorado River, and also Arizona is facing warmer winters that directly impact hydroelectricity generation during summer. As for the measures that they're taking to address this, besides the federal level policies that Catherine mentioned, they do try to require generating units to report the consumption and rates of water, but many times those are reported erroneous because a lot of the generating units do not have the adequate water meters to quantify it. And I would say that for Arizona, it might be difficult for other states to create a state level policy to address this as a more urgent matter, because Arizona does not have an independent system operator. So the three large utilities of the state are the ones that are responsible for developing their integrated resource planning, and they don't really put this as an urgent matter. However, I do want to leave you on a positive note with Arizona, because it does have a great lesson to teach the rest of the country, and that is their largest nuclear power plant, Palo Verde, uses reclaimed wastewater for cooling, and that leads them to saving significant amounts of water. And this would be something that more states would have to think and implement. As for California, as we all know, they're a leader in renewable energy. However, they still rely for their base load on natural gas and hydro. And if you look on the right, you're going to be, oh, okay, 8% is not that bad. And that is true. Compared to Arizona, it's not as bad. However, what's important to know about California is that they import about 25% of their electricity. So even curtailing a little bit of this 8% could leave their system vulnerable of meeting their peak demand with dispatchable capacity. And by 2030, they do have a renewable portfolio standard of reaching 50% of electricity generation through renewables. However, this is great, but the concern is that they're putting more pressure on the available dispatchable capacity, and that is something that California has to think through on how it's going to transition to their renewable, to more renewable energy in their portfolio. As for the reserve ratio, it might not be a surprise after all I said that this is going down steep. As you can see between their best case scenario, no curtailment, and their worst case scenario, 25% curtailment, they're basically just 2 years between 2023 and 2025. This is something that they have to address. However, the most likely curtailment scenario for California would be a 10% scenario. And this is also mostly based on California Independent System Operator reports. They already have identified that there is a significant risk of facing reserve shortfalls, and that they say that this is due to lower hydro conditions, and also because of their retiring gas that would have been otherwise online in the case of high load conditions when solar ramps down at night. And as for actions that Arizona is putting in place, there are also a leader in implementing this in their resource planning and addressing this matter. They do have a freshwater conservation policy, and they have committed of closing most of their ones through cooling power plants that are the ones that consume the most water. However, I would say that California, considering the drought and the increasing number of heat waves that are exposed, they should have even stricter policy to address this issue. And with this, I'm going to let Po talk about the findings in Australia.
Thank you. I will talk about Australia. The research on Australia focuses on the national electricity market, which is the vast grid connects the East Coast regions and all the major metropolitans, ranging from Queensland, New South Wales, Victoria, South Australia, and Tasmania. The total generating capacity is around 50,000 megawatts, and the grid is essentially isolated from other grid on the continent. That is, there's no export and import between this grid and the grids on the West Coast. In terms of electricity mix in 2020, coal and natural gas are the major source types in Australia, representing over 70% of the generating capacity. This is followed by hydro, providing around 17% of the total generating capacity, which is mostly located in Victoria and Tasmania. This electricity mix makes Australia an obvious case in the water stress in the thermal and hydroelectric generations. Based on our analysis, over 57% of the dispatchable capacity in Australia will fall under water stress areas in 2020. In fact, Australia had previously experienced the millennial drought in the past decade. In 2007, the drought and water stress had caused the coal and hydro output from coal and hydro power plants to be cut in Snowy in New South Wales and Tasmania. And in 2016, South Australia was hit by a climate shock leading to blackout because of the insufficient supply and transmission problems. And the climate issues are making the case even more severe. According to the Australian government, there's a trend toward higher atmospheric pressures on the continent's southeast region, which had caused a rainfall decrease by 11% since 1996, which also reduced the local water flow. Looking at the future decade, Australia will try to drive more renewable generation in their portfolio. However, coal and natural gas will be still playing a major role. And according to our analysis, taking into account the climate change and this electricity mix change, over 67% of the dispatchable capacity will fall under water stress area by 2030. And looking at the reserve ratio and reliability, if we take the 25% curtailment rate of water stress capacity, Australia wouldn't be able to meet its summer peak demand even now with its dispatchable capacity. In fact, the Australia Energy Market Operator have suggested there's around 8% to 31% chance of load shedding in New South Wales and Victoria. And if we take out of water stress consideration, this problem only emerge in 2028. And that's mostly because of the increase in renewable generation in portfolio and the retirement of coal power plant. If we look at the difference of the reserve ratios between these two scenarios around 0.17, as you can see on the graph. So the water stress problem is pretty obvious. Another point worth mentioning in reserve ratio about the future decades, there's two decreases in the future. One is 2022 and another is 2028. And that is the time when the two coal power plants go offline on schedule. In 2022 is the lead coal power plants with 2,000 megawatt and Valley's Point B with 1,300 megawatt will retire in 2028. So in these two periods, Australia might be even more vulnerable with these changes. In terms of policy in place, the Australia Energy Market Operator has been aware of this issue, and they outlined the integrated system plan last year in 2018. They are trying to developing a more integrated distribute energy resources strategy to enhance the coordination between all the resources. And the aim is to drive up the supply. This is the response to a more renewable generation in portfolio. However, if you're looking at the plan, there's not so much mentioned about water. In fact, Australia's water management is often a territory and state responsibility, and the energy and water policy are often developed by different government arms, and we have seen very few links between these two policy subjects at this moment. So this is a situation in Australia. I will let Tristan to talk about what's happening in Europe.
Thank you, Po. So there's going to be more graphs, so behold. So now we're going to focus on Spain. First of all, Spain is very different from Australia. It's not isolated, so it's part of the European electricity system. That means they can trade and import and export electricity. They're also part of the Iberian system, MIBO. So far, they have more than half of their electricity generation that's dispatchable, with natural gas being the biggest, hydro as well, and some coal, of which 53% are under water stress. So if we move forward to 2030, Spain decided, and it's kind of a recent law, to eliminate nuclear power and eliminate coal power. However, if that's going to happen or not, that's another question. That's the plan so far. If they do that, it's decreases the amount of dispatchable megawatt, and out of those, 57% will be under water stress. This could be an issue for Spain. They're very exposed to drought as well, same like Texas. And if we have a climate shock scenario with 25% curtailment rate of the dispatchable capacity, they could actually not be able to meet their peak demand with dispatchable capacity by 2025 and onwards. This is a big issue, especially that Spain imports a lot of electricity from France. So if that's the case, and then France is in trouble, then they won't be able to meet their demand. They have some policy in place. It's more EU level. There's the EU Water Framework Directive, and it's a river basin approach. There's also the water scarcity and droughts. However, if you focus on the Water-Energy Nexus itself, I haven't found a lot for Spain specifically in terms of cooling plants and whatnot, and this means that they should probably focus on this a little bit more. Now let's move on to France. France is a bit different than most because it relies overly on nuclear power. 71% of their consumption of electricity is from nuclear power, even though in terms of capacity that's a lot less. But nuclear is 45% of capacity mix. Once again, over half of this is dispatchable, of which 43% are under water stress. Now this is important because France is a recurrent kind of vulnerable country of climate shocks. 2003, 2006, 2009, 2013, I think, and actually even last year, 2018, they had to forego 1.7 terawatt hour of electricity because of water stress. So this is a big issue. France is also a big issue because they they maintain a lot of their power plants, nuclear power plants, in the summer because their peak demand is in the winter. But if that happens in the summer and you have water curtailment, that could be also an issue. Now, if we move on to 2030, they're going to change their electricity mix. They also plan to decrease nuclear power by 50%, so they want to close 14 power plants by 2035. This means around 6 to 8 by 2030. They also want to close all coal power plants by 2023, which shows that they're committed, obviously, to fighting climate change, but it's also making them more vulnerable if they can't meet their peak demand with dispatchable capacity, of which in 2030, 44% will be under water stress. What are the takeaways? First of all, Europe is in trouble with climate change. Over half of their basins are going to be exposed to water scarcity, water temperature increase. They say by 2031 it could increase from 1.4 to 2.3 degrees Celsius, which is an issue as I explained in the beginning. They think drought will increase by 16% by starting 2031. So for the whole system, it is an issue. For France specifically, we can see that they can obviously meet their peak demand with dispatchable capacity, but that's because they're an exporting country. If they're an exporting country, fine, but that means they can't have revenue if they want to export. On the other hand, if other countries need to import their electricity, they'll be in trouble if they have curtailment rates. So this is where everything is interlocked. If Spain and Italy is in trouble, and then France is in trouble, it could leave the whole European system kind of vulnerable. They have policies in place to kind of fix that, obviously the EU frameworks, but then they created the Aléa Climatique after 2003, and that's a way for them to really focus on trying to anticipate peak demand, but also weather patterns, water availability, and water temperature to see where they need to curtail what's going to happen in the future. This is maybe a policy we can focus on as well. So now we're probably done with graphs. We apologize that there were so many. And we're going to go on to recommendations. Please note that these recommendations are kind of for the global system, so they're kind of broad. But we try to make them applicable to all of our case studies, and these are basically the lesson learned. The first one is we need long-term planning. When you create a power plant, it lasts for decades. Usually, PPAs can be 25 years and so forth. So you need to make sure that water management is integrated in the long-term planning for the ISO, the Public Utility Commission, but also the developers themselves, the people that invest in this. We need to monitor water usage and patterns. It's done in a lot of countries. The EIA in the US is responsible for that, but there's a lot of discrepancies. For instance, 30% of water usage has not been accounted for by the EIA. And so that means there's like water that's kind of, we don't know how much it's used. A lot of power plants don't have the best monitoring system. So what we recommend is a better enforcement to monitor water usage. It's a joke. We're back to more recommendations. So another thing is lower exemptions. Why are there exemptions? Sorry about that, by the way. So whenever there's a drought and there's a water scarcity issue, typically you can't put back water into the river because it's too warm, and that can impact biodiversity and all the ecosystem. But governments, they usually have a law where they put a threshold of like, let's say 28 or 30 degrees Celsius where you can't put back the water if it's too high. But they often give exemptions to ton of power plants so that they can continue to generate electricity. What we suggest is to lower these exemptions because if we want an incentive to change water patterns and water usage and make sure that power plants use less water, we have to give the good incentive tools. Giving exemption is not one of them. There's a lot more. Forecast. We need better forecasts on the power plant level so that they can anticipate electricity demand and also weather and water usage and water availability. That's kind of a maybe more obvious one. We have to diversify the generation portfolio. France, for instance, overly relies on nuclear, and they keep having problems. So maybe the more you diversify your generation portfolio, the more flexible or resilient you can be on your grid. This is especially true for energy-only markets like Texas, where they have a small reserve margin per nature, and where maybe they won't have enough to meet peak demand if they need a lot of dispatchable energy. It might be a bit different for France, who has a ton of capacity. Finally, we want to show advanced technologies. This can be on two sides. First of all, kind of applies to the diversifying of the generation portfolio, but maybe includes DERs, renewables, but also batteries that can help create the system and make it more resilient. And we can also try and change the technology themselves of the reactors and the turbines to make them more efficient and use less water. On the other hand, we can have the cooling technologies to be more advanced and efficient. So instead of having the first ones I showed the graph about the recirculating one or the once-through technology, try and use dry-cooled system or air-cooled system to make it to kind of promote the most efficient technologies possible to cool power plants. So these are kind of our main recommendations. And now our part of the presentation is finished. We go back to our conclusion where Texas is in a lot more trouble right now and needs to address this issue faster than, for instance, Pennsylvania or France. And we invite our next speakers. So we have Mr. Addison Stark, who, as Irina mentioned, works right now for the Bipartisan Policy Center. He used to work for DOE, and he worked for ARPA, and he worked specifically for ARPA-E, sorry. And we're specifically in dry-cooled systems. So this is, I think, very relevant for us to kind of know. And then we'll have Mr. Taylor Sloan, who works for Fluence, and to explain why Fluence had this idea of really have electric grid planners integrate climate shocks in their resource planning. And he's the market applications manager, and he's the global lead for commercial and industrial market development for battery storage at Fluence. So we thank you very much. Sorry there was a lot of graph, but we hope you learned something.
Thank you all. That was very interesting and actually sets up well what I'm going to talk about now is kind of the role. So just as a quick background, and it was already discussed, I'm currently at the Bipartisan Policy Center, where I lead our energy innovation policy work. Prior to that, I was at ARPA-E, where I was a fellow and served as a program director, focusing in particular on our technological investments into dry cooling technology to really go after the heart of this challenge, which is recognizing that if there is going to be policy to incentivize more dry cooling, that we would need technology that is cost competitive, because there's a reason today why we use water to cool power plants, and I will get into that. So today, and it was kind of pointed to, 99% of US generation is water cooled, and there's 3 different approaches to that. There's cooling towers, there's once through cooling, and then there's cooling ponds where you recirculate and you manage your own water, and each of these have particular challenges. But today only 1% is dry cooled, which is essentially air cooling. Excuse me. The reason for that is because it's more expensive, both energetically and capital intensive. So today, if you're going to build an air-cooled power plant versus a water-cooled power plant, you take about a 9% hit on levelized cost of electricity, so it'll be 9% more expensive. And then depending on the temperature and time of day, you really run into very strong curtailments of the total amount of power that can come out of an air-cooled power plant, particularly during very hot times. And it gets into the thermal engineering of it all, but essentially water's a very good heat transfer medium, air is not. So you would prefer to dump your waste heat into water. So there is a little bit of work looking at hybrid cooling, where essentially most of the time you would be doing dry cooling when, say, at night when the temperatures are less severe, or during the winter when you don't have very peak temperatures, and then utilizing water or some sort of water cooling augmentation during the very peak time. So you can imagine maintaining a smaller pond to be able to supplement and cool during those times. At ARPA-E, we recognized, and we relied at the time on a lot of analysis that was done by EPRI, the Electric Power Research Institute, that was looking at kind of the impacts in climate change futures on the U.S. grid, saying that somewhere above 30% of U.S. generation capacity would be water constrained. And we recognized that we needed to focus on developing technologies to drive down the cost of air-cooled power plants. And in particular, we were focusing on leveraging new developments in additive manufacturing, new materials, and I'll talk a little bit about some of the approach we did. So we did a $30 million investment, and actually by the time it wrapped up in 2018, we did about $36 million. Started with 14 projects. I think we canceled a couple, but by the end we had about 5 or 6 viable technologies that are still ongoing after our investment. And I'll talk a little bit about this. So the way we looked at this essentially is you have a power plant where here's your turbine, and then you'd have this waste heat coming out. And usually with a wet-cooled system, you would just pump enough water through here to take that waste heat and put it away. We recognized that we needed to develop a new suite of technologies to supplement that approach. So you would imagine having a loop where you have some sort of a heat exchanger to reject your waste heat to the air. But then we started to look at other things, other innovative technologies, including thermal storage, so being able to store cool temperatures or essentially to store cold, to be able to store, capture, and reutilize water, but then also looking at other novel things like utilizing waste heat from things like the combustor, so things that are wasted out the flue gas on the top of the power plant to be able to drive supplemental cooling, and also looking at the development of advanced materials that are able to bypass this problem entirely and reject your waste heat directly to outer space, which is actually one of the coolest technologies that came out of here and has some broad-based applications for building cooling. And I'll talk about one of those projects. So give you an example of what I'm talking about. The most expensive thing about doing dry cooling today is actually building heat exchangers. It turns out that if you want to be able to do air-cooled heat exchangers, they're usually twice to 5 times the size of what your water equivalent would be, and it's built out of a lot of metal. And so it can be very capital intensive. So one of the things we recognized is there's been a lot of development in additive manufacturing technology in the last decades, to the point that you're starting to be able to imagine 3D printing heat exchangers out of other materials besides metal. So one of the projects we invested in was done up at the University of Maryland. Island, where they built a composite material where most of the heat exchanger is made out of plastic, but then you would essentially thread metal through it to be able to make thermal contact. So essentially you decrease the total amount of the expensive material, the metal, and then utilize plastic as kind of your structural material. It turns out that this has been very interesting. Then they've developed a lot of really interesting technological approaches and are currently partnering with Baltimore Air Coil, which is a Baltimore-based cooling heat exchanger company. Another approach, as I mentioned, is being able to take waste heat that comes out of your power plant, and which is usually well above, essentially you have enough thermal energy there to be able to drive some sort of an additional process. So in this case, at Colorado State University, we partnered with them to be able to then drive an additional supplemental cooling where essentially they were able to run this, capture that additional heat, and drive some sort of essentially a refrigeration cycle with it. It turns out that this has an interesting approach and most likely will be used to actually take that cooling and capture the water that otherwise would be evaporated, and then you can store that water for seasonal approaches. Similarly, at Stony Brook University, just another example of this is to be able to directly put heat exchanger, or essentially chillers, right in the stack that's coming out of the combustor, because when you combust your fuel, you're sending a lot of water vapor essentially into the atmosphere, and so there is the ability to capture this seasonally and store it. This was really focused on this was probably the most thermally intensive engineering thing, and I'm not going to get into it now because it was all about heat exchanger design, and this is not the audience. Other audiences I speak to, this could be the one we talk about the most. And then lastly, this is the one that's kind of the idea of what I was talking about developing new materials to be able to reject waste heat directly to outer space. So in 2014, there was a research group at Stanford that had published a paper where essentially they're able to build metamaterials, which is essentially materials that are structured at multiple scales, from the atomic to the nano to the macro, very precisely in that they're able to split the radiative spectrum. So the idea that you could have a panel out underneath the sun and it would reject the visible solar radiation, send it back out, but importantly, it would also radiate at local temperature and directly out to outer space. The radiation that it shot out was not absorbed by the surroundings, but actually just go directly to outer space. So you could have a piece of material directly under the sun that would be about 10 Celsius cooler than ambient temperature, essentially giving you, while the news that covered it was really bad, they would say free cooling, which, if anyone knows their thermodynamics, is really bad. You need to understand that actually there is a little bit of work going on there. But what it allows us to realize is that you can have these materials that you can manipulate surfaces and get cooling that no longer is as sensitive to things like the local temperatures. Under climate change scenarios, outer space is still at 2 Kelvin instead of 300 Kelvin on the surface of the Earth. So you have a very strong heat transfer potential. And so what this really did was we were able to leverage what they had was a scientific innovation and be able to work with them on being able to do things like roll-to-roll manufacturing. Now it turns out that these things perform really well for things like building cooling, but if you're to build one the scale of what you need to cool a power plant, you're talking about a kilometer by a kilometer big. So you're talking about essentially competing roughly equivalent with what you would try to do to build a solar plant to replace it. So while it has a lot of interesting thermal management applications, it's probably not going to scale well for power plants, but kind of tells the story of innovation, which is separately, we had one goal with what they were trying to do. It turns out that it actually really works better for buildings, which also can be water saving because a lot of buildings use water chilling anyway. And then lastly, this one's not important. It's the same. It's not exciting. The whole idea is, I should have deleted that slide. So at ARPA-E, what we did is we go out, identify a problem, and then go out and do a portfolio approach to trying to solve. There's a lot of different ways we tried to do that, through thermal storage, through improved lower capital intensity heat exchangers for dry cooling, and also novel materials and rethinking what it means to cool a power plant. These are a lot of the things that you need to try and do to solve a lot of the challenges in the energy space. Even if we have the most aggressive of policies, this is my little chance that now somebody gave me a podium. Even if we try and go after doing the Green New Deal, we can't get there with today's technology. There's a lot of real technological limitations that we have to be able to go and decarbonize the grid. And we need to be able to go out and really make innovations broad-based. And so being able to take this kind of approach is important, looking at very key pieces of what we're trying to do. Now, the other thing that we can recognize is, why do we have this problem in the first place? From a technologist's, I'm kind of a technologist scientist working in policy, so I have a very different approach. And what I recognized while I was doing this is the biggest challenge to water and cooling in power plants is the fact that there is no rational pricing for water in the U.S. Water is grandfathered, water is free, there's no way to go out and get rights, and no one pays for it. If you look at a power plant, usually they get allocated a certain amount of water a year, say 1 million gallons. So it means the price is zero up to that, then it's an affinity for the next gallon. That's not a rational way to do a market. And so, even just looking at ways to price water would be a very strong way to put technological incentives into this world. Also being able to look at things regulated, and the students in the group talked about this, being able to look at how can you get after performance limits or performance controls, technology mandates, maybe requiring certain numbers of air-cooled in different generation regions or different river systems. And then also looking at just other innovation. I talked about how do you decrease the cost of air-cooled technology, but being able to look at non-heat engine generation. So certain renewables don't require cooling, some do, and we got to be careful to understand that. And then also looking at ways to utilize your waste heat. So instead of just having to dissipate it to the atmosphere, cogen is a very viable way where you take that waste heat and utilize it to, heat a campus, or then take that waste heat and run an air conditioner for campus. So there's other ways to utilize what otherwise is waste. So think about every improvement step, efficiency improvement we have in power generation, it decreases this problem too. So there's a lot of different ways to get at it, but obviously right now we have a big challenge. So, that's it. That's my quick little spiel, and I'm happy to add some technological view on the question and answer period.
We welcome any questions at this time.
I had a question about U.S. recently they transformed. There was transition from coal power to the gas station, mainly from 2000s. Mainly electricity generation came from these combined power cycles, combined gas turbines. Was this transformation reduced vulnerability to the water stress?
I would say yes, because from our research, what I discovered is that most of the power plants that get curtailed, they're actually coal, and most of them have ones through cooling. So I would think there were very few cases of natural gas actually being curtailed. So I think that transferring to natural gas from coal, it would decrease the vulnerability, but it's still there. I don't know if anyone.
And typically, nuclear and coal use the most amount of water, and gas uses the least amount of water in terms of thermal plants. Yes.
When you speak of natural gas, are you talking about the gas that has been fracked with reportedly toxic chemicals? And if so, are those being integrated into your formula in terms of the environmental impacts that supposedly we've all read about and seen in some of Josh Fox's movies and in Pennsylvania's problems with contaminated, not just land, but farms. So my concern is, what are the implications for our small family farms? And my last question is, why can't we achieve much more with the technology we have by looking at it on a small scale? A documentary entitled Garbage Warrior, where this architect had houses off the grid made out of cob in the 1970s. Pasadena was all passive solar in 1900, and then in 1902 or thereabouts, oil was discovered, and that apparently put an end to that. So why can't we put solar panels on every home, green roofs on every home, integrate cob materials into new structures, and small turbines? In this documentary, Garbage Warrior, he had small turbines inserted under the roof. So each home integrated cob materials, wind, solar, geothermal. It doesn't seem like we're short of technologies.
Thank you for the question. We're going to take it from here. Oh, okay. So the water for fracking, we did not look that in our research. We just looked at what the water used for electricity generation. So I could not answer that. However, yeah, we know there is a significant amount of water used for that. I'm not sure if you would like to take the
Yeah, no, so there are a lot of approaches to be able to decarbonize, and distributed energy generation is an important piece of it. However, to be able to go for a full decarbonization of every home, it would be beyond the means of most incomes in the U.S. to be able to put your own generation, put your own solar. The costs are higher than the centralized paradigm that we have now. And I agree that there needs to be policy that is put forth to be able to move towards that. However, there needs to be more technological innovations to drive down costs.
Sorry, before we continue with any more question, I have to apologize. Taylor was supposed to give us some remarks. When I get nervous, I forgot about things. This is all on me. I'm so sorry, Taylor.
I thought I was off the hook.
No, you're not off the hook. Sorry about that.
Sure. Yeah, thank you. Well, first, I just wanted to say thank you to the Practicum team. I thought this was great analysis. This is really hard because not only do you have to understand electricity markets, you also have to understand water. And several of the subcomponents that went into this could have had PhD theses on them by themselves. So well done to a very complicated topic. So Fluence, we're the sponsoring client company for this project. And you're like, well, why does Fluence, who has batteries, care about the Water-Energy Nexus? And the reason is because batteries don't consume any water. Actually, batteries and water don't get along very well at all. So if we're thinking about the grid, and if a drought, a heat wave is going to coincide with peak demand because everyone has their air conditioning on, well, a gas peaker that consumes a lot of water might not have a lot of water available to actually do its job. So we're interested in it from inserting water into the planning process, finding a cost for water. You're right, it goes from 0 to infinity. That's not a very good policy. Our economists at SAIS know that the solution to everything is to have a price for it. So how can we get water attributes considered into the resource planning process and compensate technologies that don't consume water, like solar, wind, and batteries, to do the job of electricity generation, in addition to all the technologies he mentioned of actually reducing water consumption on thermal. So it's sort of two things: either reduce the water you're using or build things that don't use any water, and then price it all. I'd say that was kind of my summary. But that's how our perspective, why we're interested in it, and thanks to the team for a great job.
Thank you, Taylor.
Hi. So my question is, although your case, outside of your case studies, like during your research, were you able to find any examples of countries that were managing the water-energy nexus successfully, even in just one aspect or maybe more?
Good question. No, I think we focus on the bad stuff. But we should probably focus on the good stuff too and see if there's an issue. However, I would say, the technology is the same. So if you lose like thermal power, there's the advanced technologies are probably what he mentioned. And so you need water regardless. And we kind of know like dry cooled is better than the other one. So I guess for successful, it's like maybe where water is more abundant, but we're trying to look at where like there's going to be stress and where there's a sense of urgency. Maybe that's why we kind of narrowed the focus there.
Just responding these questions, Will. Briefly, like these water stress problems, kind of a global scale, so definitely have a lot of policy innovation, but we kind of narrowed down to these 4 regions. because through our methodology, we identify these 4 regions are the most affected. So even if they don't have a lot of policy innovations to address water-energy nexus, we kind of figure out these is the urgent things we need to address.
First, I just want to echo Taylor's comments and thanking the panel presentation. As a SAIS alum, it's great to come back here, enjoy free lunch, and also enjoy a really robust discussion. So my question mainly has to do with regional planning from the RTO perspective. So you give Pennsylvania, who's a member of PJM, a 13-member organization plus DC. You also give Arizona, which is interesting, because as you mentioned, it's the states, or it's the utilities filing their IRPs, integrated resource planning. Do you think somewhere in this discussion that the RTO or ISO or even larger transmission build-out has a role to play in the increased resiliency of some of these water-stressed generating assets, in the sense that there are 12 other states in PJM service territory that could help with some of this curtailment, whereas in Arizona might be a little bit more difficult?
Thank you for the question. So for Pennsylvania specifically, I think they're first aware of Water-Energy Nexus issue, and then the St. Lawrence Water Compact I mentioned earlier. They mentioned about like the framework that different states needs to work on, but however, I do not see like a very follow-up research or policy that directly link water energy resource together. And also under PJM's, their reports, I also don't see they have like aware of this issue. However, I will say they have very robust reaction planning regarding either cold weather or warm weather happen. And they also have the trend of increasing the deployment of solar. So I think this can be moving forward about that.
Yeah.
And maybe I'll add for the question about the ISO playing a role. I think in the French case, the RTE, the French ISO, they incorporate this into their planning as well. And so the Aléa Climatique is also with them, because it's also kind of, EDF is like the main utility there. So they work together on this issue. And so I think there's that. And also, since it's a EU system, and so definitely they work with, I guess, the EU, or they have the water directive. So I think they could do a way better job of doing this, but it's definitely a way to be able to anticipate these issues and kind of knowing where to go to in the future.
Yeah. And I would just say about Arizona, this has already been identified as an issue, and the Arizona Corporation Commissioner is trying to pass a bill that is trying to have more of a state-level policy, at least that the utilities can integrate in their planning. And as Tristan said, there are ISOs, for example, the California Independent System Operator does incorporate this. So I think it's most on like how they understand the urgency of the matter, because as Catherine showed, PJM doesn't really have a problem with their capacity right now, so maybe they don't feel an urgency, but once your capacity is starting to be affected, then you're gonna feel the need to incorporate that in your ISO.
Might just share a bit about Australia, because I want to talk about Australia's the energy system operators. They're kind of aware of this issue, but they mostly focus on reliability, not really mentioned about water, and they being aware of this because they have seen renewable energy will be driving out in the future, and they're seeing a lot of coal power plant going to be offline. And also they have been hit by some drought and climate shock before. And they are right now doing some kind of experiments, and they deployed 100 megawatt Tesla energy storage last year. And after some months of using like energy storage, electricity system operator actually give a statement saying like the battery is a good way to address resiliency, because it better respond to any unexpected condition more than conventional energy sources. So that is something happening in Australia as well.
thanks for your talk. It's very interesting. And I have question. I have a question for Mr. Stock about the dry cooling. I think it's an alternative way to like solve the water shortage problem. But I just curious that is there any requirement from the power plant side in order to install those dry cooling facility? For example, if is the power plant need to modernize themselves, or is there a scale requirement for the power plant in order to like have those cooling facility installed?
So that's a very good question, and one of the key things is when you look at a power plant and its cooling system is there's a lot of interdependency in the overall thermal management and engineering of the full plant. So you can go in and retrofit a power plant to do dry cooling, but it'll give you a larger efficiency penalty in terms of energy efficiency than it will if you design the full system from scratch. Essentially, you change the overall waste heat rejection from the turbine, and it means that the turbine would have to be resized. So it's essentially, if you change the overall thermal flow, you're operating in a suboptimal condition. So there is a lot of work going on at the large turbine designers, GE, Siemens, all these people that are really involved in power plant design, recognizing that designing from the beginning to be low water consumption is just a different power plant. So again, essentially, the goal that we had in our investments is to be able to invest in technologies that would be able to do air-cooled electricity generation with no more than a 5% penalty on LCOE. And that means essentially it could be a higher operating cost or a higher capital cost, but some way their techno-economics needed to work out that way. But there's no way to essentially do dry cooling without a penalty relative to wet cooling, assuming that water's free. And so that was kind of the sense. And there is a lot of need to engineer the full power plant to do it to be most cost-effective possible.
Did you have like a break-even water price where the two technologies would be equivalent?
We didn't take that approach because we're a technology development agency and we don't essentially influence policy. I'm trying to remember when we looked at it, and I'd have to look back into it, but I think it was not very expensive. Like, I mean, we're talking, so if you look at desal water, what is that? That's something like 2 cents a gallon. I think we're on the order of magnitude of the cost of desal. So like low relative to like the extra fuel you would burn in a inefficient power plant design.
That was a really great presentation and a very important topic, so thank you for presenting on this. I heard them mention that there was a modeling based on RCP 8.5, which has been pointed out as quite a bit more intense than some of the other scenarios that have been modeled. So I was wondering if there was going to be any like sensitivity modeling or sort of looking at this in a different pathway and kind of how that might affect some of the results, and just for general comments on that. Thank you.
Well, so yes, I think what's hard with this is like if we looked at any type of model, there was going to be like a lot of assumptions, and basically it's really hard. Like if you look, and it was good because it was global, and so when we try to do more research, sometimes we were more specific, and there was one specifically for Europe, and they had some values, and then we had specific for other regions that had some values. So I think to try and be coherent, that's why we kind of chose this, even though it is maybe more intense. But I think it's what we're trying to do here is really like if there's one day of climate shock, for instance, how is the grid going to be maintained and resilient? So it's more about thinking the worst case scenario. And I don't think it's bad to use maybe more the worst case assumptions, especially that problems have occurred in the past. So it's not as if it's like out of the blue. That'd be my say. But.
I mean, like when you analyze like water vulnerability of power station, you took only like thermal power station. But what if the country like running like, for example, base load on thermal power station or like nuclear power stations and peak load on hydroelectricity? And if it comes together, like water vulnerability level will be high. I think like, for example, I think France, like nuclear provides mainly base load and hydro and some like coal station, gas stations provide peak load. And for example, if peak load comes from hydroelectricity and there is not enough like physically volumes of water, like will be that like total grid vulnerability, I think, higher?
So we definitely took this into account. The fact that we used a percentage of like the hydro plants that were in water stress areas, and then the same thing for thermal. But I would say for France specifically, if nuclear is in trouble, hydro is probably also a little bit in trouble. It's kind of related. So, if there's a drought kind of like all of southern France. So even though you want to meet peak loads, you may have to have, and base load is affected with nuclear. I think it's still going to be hard to meet some peak load. And we have crazy numbers of like hydro going down, like, from year 2016 to 2017, hydro went down 49.1%. Because of like water variability. And if you include like a year of bad rainfall, which was 2017 in France, 40% rainfall decrease. So in that case, if nuclear is in trouble, I guess we can safely assume, and that's my view, that hydro may be in trouble as well.
I actually also have a question. Not for myself, of course, but for Mr. Stark. I was listening on a hearing on ARPA-E a few weeks ago, and they were debating the budget for the next years. And as you mentioned, we cannot really decarbonize our energy system without more innovation and reducing the cost. So I was just wondering on how do you see the investment in more innovation going forward? Are you positive about it? Or?
Yeah, so this has become a little bit of a dance every year for the last 3 years that the president requests zero, and then we are happy to see that there's strong bipartisan agreement on the Hill, both bipartisan and bicameral, support for innovation for a variety of reasons. There's environmental goals, meeting climate change challenges. There's international technological competitiveness, which resonates strongly on the right and has when the word climate change was not really something they said. What we've seen now is politically there's been a shift among moderate Republicans, particularly among Senate Republicans, that they want to move away from science denialism. You look at Senator Murkowski and her leadership of the Energy and Natural Resources Committee. You look at a lot of her colleagues, including even people from coal states like Barrasso from Wyoming, that they are interested in a new lane, which they're calling innovation, not regulation. Now, it's a different approach. However, it's a big step forward. And certainly we know that innovation needs to be done to give us the technologies to be able to essentially implement regulatory regimes with minimizing cost. So if you do want to go out and tax carbon, you want to be able to have technologies available to be able to decarbonize as far as possible at a given price. So, we know that we're looking to take advantage of this moment. We know that we don't know. We believe that there's a lot of bipartisan support for innovation lines at DOE. And, that's what I do in my role now, is being able to really push this innovation agenda and being able to maintain the support bipartisanly, because we know at the end of the day it's 60 votes to get anything done. And particularly in this issue, we want to make sure that we see sustained support. So I'm optimistic. But, I've also staked my career on energy innovation, so I've got to be optimistic.
Okay, so thank you for closing on a positive note. And if there are not any questions, thank you all for coming.